Hey students, welcome back. This is Torres, elbow bump. How are you? Are you doing okay? How's your family? Are they doing okay? Remember, if you need anything, please send me an email so that I can try to help in whatever way I can. So lucky you, you get to hear my voice for another lecture, but the best part is we're going to be putting everything that we learned together about the Central Limit Theorem and the sampling distribution for proportions to find the probability of an event. Yay! We've discussed various key theories in the last few lectures. First of all, we discussed how we will never be 100% sure of the population proportion because we might not have access to be able to measure the truth, as we can use estimates to try to infer what the true population can be, the true population proportion can be. If we're working with a sample, then we need to make sure that some basic conditions are met so that our sample can be used in this inference. And there are certain conditions that will allow us to know if the sampling distribution of our sample proportion is close to the normal distribution. In order to use our sample, then we need to know that these three conditions of the Central Limit Theorem must be met. First, the sample has to be collected randomly and the trials have to be independent of one another. Second, there has to be a large sample, meaning that the sample has to have at least 10 successes and the sample has to have at least 10 failures. The last condition is that there must be a large population, that the population size has to be at least 10 times larger than the sample size, so 10 times the sample size. If those conditions are met, then we can infer that we have a normal distribution. And as a reminder, the thing about the normal distribution, the probabilities are known. If we have a normal distribution, approximately 68% of the values will lie within one standard deviation before and after the mean. Approximately 95% of the values will lie within two standard deviations before and after the mean. And approximately 99% of the values will exist within three standard deviations before and after the mean. A normal distribution's characteristics are that it's unimodal, it's symmetrical, the tails are approximately the same length. If we were looking at the numerical values, we would see that the mean and the median are approximately close to one another. The skewness statistic is between -1 and +1, and the kurtosis statistic is between +3 and -3. Okay, those are all things that we're going to use over and over and over again. So if you're having trouble remembering these, make yourself just a little sheet or a little post-it and always have it in front of you. It's important to have a very strong working knowledge of those concepts in order to be successful in everything we do moving forward. If we have a sample proportion, right, then we can infer that our sample proportion, p hat, is approximately the same as the population proportion, p. If we know the population proportion, then we can use this formula to figure out the standard error. A lot of the times, and I would say most of the time, you don't know the population proportion. It's unknown. So you have to substitute your sample proportion, which is p hat, into this formula to find an estimate of the standard error. So we're going to go ahead and start putting all this information together, working with the Central Limit Theorem to test for normality, working with what we know about the sample proportion and the sample's standard error or estimate of the standard error, and then using what we learned about probabilities to find the outcome of an event. In order for you to be able to participate in this section, or in order for you to practice, you're going to need the following things. You're going to need pen or pencil, something with which to write, paper, a calculator, and some sort of technology that will help you calculate probabilities. You can use the one that is in ePortfolio, that's an Excel file, or you can also use StatCrunch. Also, if you have a probability diagram, like the one that will be linked in the description box below, that's just the bell curve with all the probabilities inside of it, or all the percentages under a curve inside of it, that's always helpful to have too. For this first example, we're going to be talking about vegetarians. So it says, according to www.statisticbrain.com, 59% of vegetarians are women. Suppose a random sample of 500 vegetarians is taken. What is the approximate probability the proportion of females in our sample will be more than 63? All right, so right here, we know that we're talking about a population proportion. They've actually done some sort of statistical comparison. As far as we know, this is the population proportion, or it's at least the sampling proportion that statisticbrain.com did. Okay, we're not taking the sample. But they want to know if this is true and you were to take a sample, what is the probability that the proportions in your new sample of 500 people will be more than 63%, will be a lot bigger than this 59% is what we expect. Okay, so what's the probability of that happening? So here's my problem. It doesn't say anything about the condition being normal, so let's go ahead and start off by checking the conditions of the central limit theorem. So I'm going to go ahead and check the conditions for the central limit theorem here. My parameter is going to be 0.59 because this is the population parameter that I'm given, and I just wrote this in terms of a decimal. I have a sample size of 500. Okay, and I'm going to go ahead and check the conditions of the central limit theorem. First condition I'm going to check is that this is a random and independent sample. Well, it says it's random. It doesn't say it's independent, but I'm going to go ahead and assume that. So random and independent, check. Number 2, I'm going to check to see that my successes and my failures are both greater than 10. So for my successes, I'm going to multiply my sample size times the proportion. So I've got sample size of 500 times the proportion of 0.59. I'm going to go ahead and drag my calculator over here. So here's my calculator. I've got 500 times 0.59, and I get 295. So my successes is 295. Is that greater than or equal to 10? Yes, check. Okay, so if 295 are successes, then the difference has to be my failures, right? So let me go ahead and pull up my calculator again. So I've got 500 minus 295, and I get 205. So my sample size times a whole minus the proportion, so it's really just everything else, is 205. And 205 is greater than or equal to 10, so that checks out too. The last one is I need my population size to be 10 times larger than my sample size. So for population size, it's all vegetarians. So this is millions of people. And 10 times my sample size is the same as 10 times 500, and that's the same as 5,000. So millions is much greater than 5,000, so all three components of the central limit theorem check out. Check, 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 check. Perfect. Checks out. I'm good to go. Okay, so now I can assume normality. Now what I need to know the dispersion of that data. I need to know the spread of that data on my normal curve. So if I've got my normal curve right here, we can already assume that this thing is going to be normal. I know my mean and the median are going to be here in the center. Okay, here's my z-scores, 0, 1, 2, 3, -1, -2, -3. These are my z-scores, okay? And I know that my sample proportion, or my population proportion rather, my population proportion is going to be 0.59. So that's going to go in the center. But what I don't know is this distance right here. I don't know how spread out that is. All right. So let me just scooch this up a little bit. And since I'm working with proportions here, I'm working with the population proportion, or what they believe the population proportion to be, 0.59, then I can figure out my differences here, my standard error, by using this formula. Awesome. Let's go ahead and plug this in. P is 0.59 times 1 minus P, which is 1 minus 0.59. Go ahead and extend this out. And this whole thing is going to be over 500. Okay, let me grab my calculator again. So here's my calculator. And I'm going to go ahead and clear this out. So I've got 0.59 times parenthesis 1 minus 0.59 equals. I've got a number. Okay, that gives me my numerator. Now I'm going to go ahead and divide it by 500. Divide 500 equals. Now I've got everything underneath the radical. Now I've got to take the square root, and I can do that by hitting square root and then answer equals, and I get my standard error is approximately 0.02199. 0.02199. Let me just double check that I remembered that number correctly. 0.01995. I'm just, you know what, I'm going to go ahead and just write everything out. Let's see. 545407. 545407. Okay. Now, why did I expand this out instead of rounding? I could have rounded, but what happens when you round? You're introducing little tiny bits of error that will actually catch up with you. Okay, so now this is saying that this is approximately 0.02. This distance right here is 0.02, then this is going to be 0.61, and this is going to be 0.63, and this is going to be 0.65. And if I go in the opposite direction, I'm going to get 0.57 and 0.55 and 0.53. Okay, now these are just rough estimations, but it helps me figure out what's happening here, because now I can go ahead and look at this, and it says what is the approximate probability that proportion of females will be more than 63%. So 63% is about right here, not exactly, but it's about right here. And since we want everything that is greater than 63%, I can color everything that is to the right of 63% or 0.63. So I'm basically saying how much of my curve is colored here. What percent of my curve is colored here? If I know what the percent is that is colored, I will know the probability. So this colored section is the probability. And it's also the area under the curve, because the area under the curve is a model of the probability. Okay. So let's see what I did. First, I checked the Central Limit Theorem. Then I went ahead and figured out what my curve looked like with my proportion, my population proportion, or the expected population proportion in the center, right? It's the one that was given to you. Then what happened? I needed to know the spread, so I needed to figure out how far this distance was. I used my standard error formula to figure out the spread, put it into the calculator, and I got that the spread is about this. Okay, this is the number not rounded, but I rounded here in order to just make a model. So I went ahead and used this curve to make my model. I went ahead, just as before, added up the standard error, in this case standard error, over to the right, and for every standard deviation I went to the left, or for every deviation I went to the left, I subtracted 0.02. Then I went back and it says, what is the approximate probability that the proportion of females in our sample will be more than 63%? I want to know how much this is colored. So I can do this a couple different ways. Let's do it with StatCrunch first. So I can go into StatCrunch, and I can go to where it says Stat, Calculators, and of course we want normal. Okay? It's going to give us mean, standard deviation, and then we can decide if we want it to be greater than or less than a certain number. Okay? Now, although this says standard deviation, right, it could have said standard error. Maybe a better little label for this might be deviation. Like it might be just differences or spread or something like that. So our mean in this case, what number was in the center? 0.59. Okay. Our standard deviation was a long one. A standard deviation was, what was that thing? I'm going to go ahead and check. 0.02199. 0.02199. Okay. I'm just going to go ahead and leave it there. Now, keep in mind, since I rounded here, I've got a little bit of error, not a lot, but there's a little bit there, and it just keeps adding up. So, you know, not a really great thing to do, but we're just trying to be fast here. Now I want to know, what is the probability of something greater than or equal to 63%? Okay. If I did this correctly, I should get a curve with just that little right piece of the tail, right, colored red. Boom. Look at that. It's right here. So it says the probability is 0.03445. So I can go back here and say that the probability of P being greater than 0.63 is 0. I already forgot what it was. 0.03445. Or approximately 3% chance, right? That's the same as saying there's 3.445% chance. As always, I link the Google Slides in the description box below, as well as in Blackboard. So you could also take a look at the slides to get an idea of how I did the math. This is just a summary of everything that I did on Ziteboard. Same thing, to find the probability that proportion in the sample is greater than 63, we use that model that we created, that we assumed to be normal. That's what this n means. That the mean was 0.59 because that was our expected population proportion. That's what we believe the true population proportion to be. And the standard error is 0.022. Okay, now here it's rounded. The more you round, the more error it is. And we want to know, what's the probability of something being greater than 63%. We can use StatCrunch in order to figure that out as well. And here is the exact same thing that we saw in StatCrunch. So it says the probability of the proportion of females in the sample will be more than 63% is only about 3.45%. So it's a very small possibility of that happening. That if you were to draw a random independent sample for your own study, that there would only be a 3% chance that from your random sample, more than 63% of the people in the sample will be vegetarians. Let's do another example. This one says, in a closely contested school bond election, polling indicates that 50% of voters are in favor of the bond and 50% are against the bond. Suppose a random sample of 80 voters is selected. And then it says, what percentage of the sample would you expect to favor the bond? Does the Central Limit Theorem apply? What is the standard error of this sample proportion? If so, what is the approximate probability that the sample proportion will fall within 2 standard errors of the population value 50%? Okay, so I'm going to do the same thing as before. Go ahead and read this out, figure out what I know, and start answering the questions. So looks like they did some poll and 50% of the people were in favor of this bond and 50 were against. So according to their poll, they're saying that the true population proportion in favor or against, right, is 0.5. Awesome. And now I'm going to take a random sample of 80 people and do my own experiment. The first question says, if you take your own sample, right, your random sample, what would be the percentage that we would expect to favor the bond? Well, in my sample, I would also expect that 50% of them would favor the bond. So my p-hat is going to be also 0.5. It's going to be the same. There's no reason to believe that it's not going to be the same. Now I'm going to check the conditions of the central limit theorem. The first one is random and independent. Well, it says it's random, but it doesn't say it's independent, but I'm going to go ahead and give it the benefit of the doubt. So I'm going to go ahead and check, say check. All right. Next one says that I need to have the right sample size. I need to have a large sample size. So to check my sample size, I need to multiply my sample size times the expected proportion. My sample size is 80 and my expected proportion is 0.5. So if I were to go ahead and do the math on that, 80 times 0.5 is 40. Is 40 greater than 10? Yep. So that checks out too. Now I need to know if these are my successes. I need to know my failures. I've got 80, 40 of them are successes, so the other 40 have to be failures. I can also use the formula and times a whole minus the proportion, which is just 80 times 1 minus 0.5, which is the same as 80 times 0.5, so I get 40 again. And is 40 greater than or equal to 10? It is. So that's a big giant check too. Check. The last condition of my central limit theorem says that my population has to be at least 10 times bigger than my sample size. So I need to know that my population, which is voters, is at least bigger than 10 times 80. So voters, it doesn't say how many voters there are in this town, but as long as the town has more than 8,000 voters, I'm okay. Let's just say that there's 25,000 voters. There's a lot more than 800. So as long as the voters are more than 800, I'm okay. So assuming that's true, then I have met all three conditions of my central limit theorem, and I can assume normality. All right. Let's see what I got. All right, so here is my diagram. This is 0, 1, 2, 3, negative 1, negative 2, negative 3. My center is going to be 0.5. Now I need to find how long is that spread. What is that distance right there? Okay, I'm going to go ahead and scooch this. Scooch, 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 scooch. And I'm going to use my standard error formula to figure that out. Okay, this time I'm actually going to be using my sample. So I'm going to be estimating what the standard error is here. So I've got SE equals big radical p hat 1 minus p hat divided by 80. Okay, so now I've got 0.5 times 1 minus 0.5 divided by 80, and then take the square root. So let me grab my Google calculator again. Clear this out. I've got 0.5 times parenthesis 1 minus 0.5 equals, this is my numerator. Go ahead and divide by 80. Gives me everything underneath the radical. And then take the square root, and I get that my standard error, my estimated standard error for my study is going to be 0.05590169943. Right? I could have rounded this, but I'm not really done yet. Okay? All right. So now I've got to figure out, so this is my standard error. I know that this is, if I'm going to round this, let me just round this to 0.06. Now this is just to create a model. What I'm doing now is I'm just creating a model to see how this is going to sort of look. This is not a calculation, it's just strictly for my visual reference because it helps. So if this distance is 0.06, then this distance right here is going to be 0.56. Then another one is going to be 0.62. And then another one is going to be 0.68. And if I subtract 6 going in the opposite direction here, then this can be 0.44. This is going to be 0.38, and this is going to be 0.32. Okay, so this is kind of how, just a rough, loose model of what this thing looks like. Okay. Next question says, if so, what is the approximate probability that the sample proportion will fall within 2 standard errors of the population value, 0.5? Well, 2 standard errors on either direction of 0.5 is here. Let me do this in red. Is here. And here. This looks familiar. This looks about 95%, doesn't it? "95% of all values lie within 2 standard deviations of the mean." That's what I've been saying over and over again. So what is the approximate probability that the sample proportion will fall within 2 standard deviations before and after the mean? 95%. Just as in the vegetarian example, I've gone ahead and given you the slides with all the information as well. This information has the exact same information that you'll find in the Ziteboard that I've linked below as well. It tells you that we've checked the conditions of the Central Limit Theorem. We can assume that our data is normal, and we can use the proportions, and meaning that this is a normal distribution. Our population proportion is 0.5, and we've figured out the standard error as 0.059, and remember, ours just kept going over and over again. Because we know the empirical rule, we know that the probability of the sample proportion will fall within 2 standard errors of the sample proportion is 95. So we could do this using technology. I'm not going to get into that for this example because I really want you to start like kind of using what you've already known. But here in this case, what this is saying is that we have the 50 in the center, and then you've added 2 standard deviations to go to the right, and you've subtracted 2 to go to the left, and you found what those values would be. And that's what we did when we made our model. And then it just tells you that the probability would be 95%. Our last example has to do with the American Veterinarian Medical Association and dog ownership. According to the American Veterinarian Medical Association, 36.5% of all Americans own a dog. Suppose a random sample of 200 Americans is taken. Would it be surprising to find that 45% of the sample owned a dog? Why or why not? I'm going to go ahead and follow the same steps as I did before because this is the way things make sense to me. Okay, so I'm going to go ahead and start off by reading my question carefully. So it says, according to the American Vet Medical Association, 36.5% of all Americans own a dog. So according to their study, they believe that 36.5%, and another way of writing that is 0.365 of Americans own a dog. And I'm going to go ahead and take a random sample of 200 people and see what's happening with that one. Okay. All right. So first, let's check the conditions of the Central Limit Theorem. Number 1, random and independent. I'm going to do the same thing as before. It does say that it's random, and I'm just going to assume that it's also independent. Number 2, I need to make sure that my sample size is large enough. So I'm going to use the sample size times the expected proportion, 200 pet owners, I guess, and I'm going to multiply that by 0.365. I'm going to drag my calculator over here, clear it out, clear. 200 times 0.365 equals 73. So if I've got 200 people, it's expected that I will have, so is 73 greater than or equal to 10? Yes, it is. So this is looking good. Okay, so that's my successes. Well, if in my sample I expect 73 people to own a dog, then I would expect everybody else not to own a dog. So I could just subtract 73 from 200 and get 127, but just to do things mathematically so you can see how this works, I can also just write out my formula, n times 1 whole minus the proportion, and I would get 200 parenthesis 1 minus 0.365. I'm going to go ahead and drag over my calculator. Clear this out. 200 times parenthesis 1 minus 0.365 equals 127. So I would write equals 127 is greater than or equal to 10, and those would be my failures. These two check out, so check. The last condition is that my population has to be at least 10 times bigger than my sample size. So I've got my sample size is 200, so 10 times my sample size is the same as 10 times 200, and that's the same as 2,000. And are there at least 2,000 Americans? Yes, there's actually like 365 million Americans or something crazy like that. So this is a lot bigger. So all Americans is a humongous number that's greater than 2,000. So my last condition checks. Oops, wanted that to be green. Check. It's still not green. Success. So I can assume normality. Okay, yay, it's normal. Let's see what this means. Okay, so here I'm going to go ahead and draw my normal curve. Z-scores 0, 1, 2, 3, -1, -2, -3. My expected proportion is 0.365, and I don't know this distance, but I can calculate it using the standard error formula. So here's my standard error formula. And I'm going to go ahead and scooch this up. Okay, let's go ahead and plug everything in. let's see, my square root of 0.365 times 1 minus 0.365, all divided by 200. Great. Let's grab my calculator. Clear it out. 0.365 times, parenthesis, 1 minus 0.365 equals, there's my numerator. Go ahead and divide by 200 in my denominator. I get everything underneath the radical, and then take the square root by hitting radical, answer equals, and I get that my standard error is 0.03404. Great. So this distance right here is approximately 0.03. So let me go ahead and make myself my little model here. I'm just going to scooch this down a little bit here so we can see it a little bit better. And I'm going to add 0.03 moving up, and I'm going to subtract 0.03 moving down. So here I'm going to get 0.395, and here I'm going to get 0.425, and here I'm going to get 0.455. In the other direction, I'm going to get 0.335, subtract 0.03 again, I'm going to get 0.305, and subtract it one more time, I'm going to get 0.275. Perfect. Okay. There's my model. Now I have something to work with. Now it says, would it be surprising to find that 45% of the sample owned a dog? So where's 45%? 45% is way up here. It's way up here. So would it be surprising? Yeah, it's going to be really surprising. There's a very small possibility that 45% of the sample owned a dog. Let's find out exactly what the probability is of 45% of the people in your sample owning a dog. We're going to use the same StatCrunch program. Our mean is going to be the expected population proportion, so that was 0.365. Our standard deviation, and it wasn't the standard deviation, it was the standard error, was 0.034042. Just gonna, and we want to know what is the probability of 0.45 of people owning a dog, so more than 45%. And the answer is, look at that tiny little bit. It's not even 1%. Very, very small possibility. Just as in the last example, I have all the slides detailing everything. Again, this is exactly like it is for the Ziteboard. So the Google slide link is in the description box below, and the Ziteboard link is also in the description box below. So you'll have both in order to help make sense of it all. So what's the big idea? Today's big idea is that if the conditions of the Central Limit Theorem are met, you can assume normality. And that normality can describe the sampling distribution. That sampling distribution can be used as a model to find probabilities of events. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there's new videos for this course. Okay? This is your teacher, Torres, saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!